Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 1026, maximum difference between node and ancestor. In this video, we are going to share two solution formats based on traversal. First, I'm going to read through the problem statement to digest the requirements. And then we do the analysis, and finally we share the code. First, the problem statement. Given the root of a binary tree, find the maximum value v for which there exist different nodes a and b, where v is the absolute difference of the values of the two nodes, and they must have a ancestor and descendant relation between the two nodes a and b. So the next paragraph explains what do we mean by a is an ancestor of b, right? So with that said, let's look at the examples. So for example 1, so the output is 7. Actually, you can look at 8 and 1. So this has a difference 7. So this is the maximal according to the problem requirement. So you can see that here in the tree, 1 is the smallest value, and 14 is the largest value. But the absolute difference to return is not 14 minus 1, 13. The reason is that 1 and 14 do not form a descendant and ancestor relation, right? So this is example 1. So now let's look at example 2. So in example 2, so this is very special because this tree, actually from the starting point 1 to the leaf 3, there is actually a unique path. So the minimal value is 0. The largest value is 3. So the difference for this example is 3. Because there is only one unique path from 1 to 3. So any two nodes on this path must have a ancestor and descendant relation. So that's the difference of this one with the first example. The first example and the second one actually forms representative test cases for this problem. So before we do the analysis, let's also look at the constraints. First, the number of nodes in the tree is in the range given by the closed interval. One end is 2 and the other end is 5000. So here 2 because it guarantees that there are at least 2 different nodes, and 5000 is an upper bound, so which actually quantifies the problem set's upper bound. So secondly, the node values are non-negative and are bounded above by 10 to the power 5. So that's actually not that essential for the methods to solve this problem. So with that said, we are ready to do the analysis. So for this problem, I guess that the important thing to notice is the following observation. So A is an ancestor of B, or B is an ancestor of A, is equivalent to that there exists a path containing A and B, right? So we actually do not need to know the details of whether A is a descendant of B or vice versa. So we can just update according to their absolute difference, right? So because the absolute value, so A value minus B value equals B minus B value minus A, right? So with that said, so here once we grasp the above observation, so we just need to compute the maximal value difference along each path during traversal. When we finish the traversal, so we also obtain the global maximal difference. So that's our all guiding principle. So with that said, we are ready to do the analysis. So actually we have practiced quite a large number of traversal problems based on the trees or graphs. So writing the code here is actually very straightforward. So first, I'm going to write a solution based on recursion. So with recursion, so for this, I'm going to introduce an attribute. Let's call it answer. So originally it to be 0, right? Because absolute value is always non-negative, so we can set this to be the smallest possible one. Because we want to find the maximal one, so we want to update. So we need to set a priori with a minimal one. Then we are going to write a function to do the depth first search, see, or I can just see traversal, right? So let me write like this. So node. So here I'm going to write a minimal value. Let's say a or minimal, or b is a maximum, right? So this is what we intended to interpret. And then we are going to do this if node. If not node, actually we just do not do updates, right? So if node, so actually we want to update a and b. So a and b will be the minimal, because a corresponds to minimal, the pre-minimal value and the node value, right? And the maximum, so it's the pre-b and the node value, right? So this way, during the traversal, we can actually record the maximal or minimal along the path. And then we are going to update the result to be the previous one and then the difference between a and b. Because we write like this, b is the maximal and a is the minimal. So b is always no less than a. So we can write b minus a directly here without using the absolute value. And then we are going to do the traversal for a left subtree and right subtree, right? So dfs node left, and then so the minimal will be a and will be b. So notice that a and b have already updated. So similarly we do for right subtree, right? Up to now we know the minimal is a and the maximal is b, right? So this is a hyperfunction. So this hyperfunction, you can understand it as a worker. So when we call this function, it's going to update the attribute answer, right? So with that said, we are ready to call this function. So dfs. So the node is replaced by root. So the maximum value, I'm going to set it to be minimal value to be infinity, positive infinity, right? Float to be negative infinity. So this way, at the very beginning, so you have a minus b will be negative infinity, right? It's less than answer, so right. So this way, we can finish the update of the answer attributes, and then actually we can do this. We can do self answer. So this is the one solution format. So let's do a check, and then so here answer is not defined. So let's see self ans here self answer. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So this is one version of solutions. So let me copy this function signature and make a slightly modification. So if you are not customer to use the attribute, so you can use the variable answer, and then you just use non-local answer, right? So here you can just use answer and use answer. So then this always also plays the role of updating this variable, right? And then we call this one, and then we return the answer variable. So now let's do a check. Yeah, it passes the first example, I guess. So now let's look at the generic case. Yeah, it passes all the generic cases. So this actually there's two versions. So let's still call it v1 prime. So these two versions are actually the recursive version. So next, I'm going to copy this function signature and give a solution based on iterative format. So here without recursion. So in this iterative format, so we could do depth first search or breadth first search based on our needs. So here I'm going to first initialize a container. So let's call it stack. So stack will correspond to depth first search. But if we use this list as a queue, it corresponds to breadth first search. So let's first write a solution using depth first search, and then we comment on how to make it a breadth first search. So for this, I'm going to store 3 pieces of information. First, the node itself, and the second, the maximal, and let's see, I'm going to write like a float infinity. So I'm going to write a negative infinity. So this corresponds to the maximum, right? So then float infimum. So it's corresponding to the minimum. So here, what we store in the stack is node, current max, and min, right? And then what we're going to do is to initialize an answer variable, right? And then we do the standard traversal. So this while loop, while stack. So depends on how we do append or a pop from the stack. We can have breadth first search and depth first search. So here I'm first going to write a depth first search traversal. So I'm going to get this information first. The node, the max so far, and the min so far will be stack pop. So pop from the head, in other words, the tail. So in this case, so let's compute the min so far. The min so far will be minimum of the min so far and the node value, right? So same as in the first two solutions. And the max so far will be max, the max so far, and the node value, right? So then what we are going to do is to update the answer. So here we are going to update. So there are several possibilities. So first is the original state of the answer, and secondly will be the absolute value, so of min so far minus the node value, right? So another possibility is absolute value of max so far minus node value. So anyway, the maximum difference will be appear in this variables, or these three choices. So once we do this update, and then we want to continue, right? So we check the node for information. So here I'm going to first try this one. So this corresponding to pre-order traversal, right? So first check node right, and then check node left, right? But for this problem, you can also check node left first, but in a rigorous sense, that will not correspond to pre-order traversal. So with that said, let's do this. So we're going to stack append, right? So this is the tuple, so node, all right, and then max so far and min so far. So this is one, right? Now let me copy this part, and I'm going to do this. So I'm going to change this to be left. So the max so far and min so far does not change. So after our traversal, we're going to return the state of the answer. So that's the second solution format, right? So essentially it's the same as the first one. So so the overall idea is still based on the observation that A and B have an ancestor descendant relation if and only if they are in the same path. So with that said, we are ready to do a check. Yeah, it passes the first example. Now let's look at the generic case. So this solution actually corresponds to the depth first solution. So here actually corresponds to the pre-order traversal. Notice that in the pre-order traversal, we check node right first and then check node left. But for this problem, the order is not important. So if you put this node right and below, in other words, you check the left first, so it still works, right? So that's one comment. Let me revert back this one. So because I want it to correspond to a rigorous pre-order traversal. This is the one comment. So another comment is that so we can actually pop from 0. So in this case, if we put the left or right left in front, first check left node, then check right node. So this will correspond to a breadth-first search. So for breadth-first search, but here is okay, you still can maintain this relation, but in a not very rigorous sense. So this still works, right? So also you can, so here there are several flexibilities. You can change the check for order of right subtree and left subtree, or you can select how to pop from the beginning or from the end, or you can see you can put in the front or at the tail. So in that way, it's better to use a deck, right? So that's their structure brings us a lot of flexibility. So with that said, actually we finished the second solution format without recursion. So I guess that's about it for this problem. So in this video, we shared two formats of solutions based on traversal, and the key for this problem is this observation. So actually we have practiced quite a lot on binary tree traversals. So you are welcome to check out the corresponding videos and other videos in our playlist and our channel. So with that said, I guess that's about it for this video. Thank you.